Welcome back, folks. Today we're going to get going with lesson 4.4 on related rates. Now, this is going to be a lesson we spend several days on. We're going to break into multiple parts. Today we're going to take our part one, just get through a few questions and kind of get this stuff going. So here we go. All right, so problem one, let's just dive into a related rates question. And I try to start off with a simple example where both the situation and the calculus is simple, just so we can kind of get a feel for, get a general idea of what we're doing. Let's say that a pebble is dropped in the middle of a pool of water, which creates a circular ripple. Okay, so the situation we have is we plop a pebble into a pool of water here, and there's going to be some ripples that extend out from that center. Okay, we've got a simple situation here, but we could generalize this to talk about a sound wave, talk about maybe a disease spreading out in a larger city from a point of origin. Okay, how big is the nuclear blast coming from that initial spot? Okay, so simple situation, but a lot of different contexts we could kind of apply it to. Okay, it says that the radius of the ripple is increasing at a rate of 1 centimeter per second. At what rate is the area of the circular ripple growing when its radius is 3 centimeters? Okay, now the reason we call this a related rates question is we have two different rates, one with the radius, the other dealing with what we want to know, the rate of the area of the circular ripple. And typically one of these would be something that's easy to measure. Okay, if I want to find the radius of a circle, that's fairly straightforward. It's a little more difficult to find that area, much less the rate that the area is growing. Because as you can see, when that radius is small, it's not growing as much as when it's bigger. Okay, so simple related rates situation here. Okay, first thing we're going to want to do is put what we're trying to solve for in terms of calculus notation. We want the rate that the area of the circular ripple is growing. Okay, so I want a rate of an area. Now, if we could use a capital A to stand for area, the rate of that with respect to time would just be dA over dt. Okay, so that's what I'm looking for with this problem here. I want to find the derivative of A with respect to t, so as time changes, how much is that area changing? All right, to do that, first thing we're going to want to do is list what we know. Okay, what we know about this situation here. And this one's fairly simple. We have both a radius and then the rate of the radius. Okay, and future questions will be more complicated, more variables, more stuff happening. But like we said, starting off simple here. We want to figure out the dA over dt when the radius is equal to 3 centimeters. And this rate here, the radius is increasing at a rate of 1 centimeter per second. What I do then is that is the derivative of the radius with respect to t is 1 cm per second. And to make these problems work, typically what we're going to need is both the dimension, the value, and then also its derivative, okay, to apply that to a problem. All right, so list what we know, and this could be open-ended. There might be other things I solve for as I go through. And then the next thing I want to do is come up with an equation that relates both my area and my radius together. Well, that's just the area of a circle formula, A equals pi r squared. And what I should be able to do with this is take derivatives and get this dA over dt. So a step you aren't necessarily going to have to show every time, but what we're doing is we're going to take the derivative with respect to t on both sides of this equation. All right, not in terms of x. There's not even an x in this context. We're taking the derivative as far as t is concerned. Okay, so as the time changes by a second, what's happening to the radius or what's happening to the area? All right, and the derivative of a with respect to t is just dA over dt. which is what we're looking for with this one. For the derivative of the pi r squared, okay, we've got the constant pi, we can leave it there. Finding the derivative of the radius is just, radius squared, sorry, is just using my power rule, 2r. And then since I am finding the derivative in terms of t, not in terms of r, what I will need to do is use my chain rule in the form of implicit differentiation. I'd have to multiply it by dr over dt. Okay, because again, we're finding the derivative with respect to t, not r. All right, that's it for the calculus. Once I have that derivative taken care of, what I can do is just plug in my different values. So we can finish this off by saying dA over dt, okay, the change of area with respect to time, is going to be equal to the pi times the 2 times r, the radius, which we're looking specifically for when the radius is 3 centimeters. So we'll say 3, and I'm going to include the cm on that. All right, times dr over dt when the radius is 3. We're given that's equal to a 1, so we'll write that as 1 cm per second. Okay, with a lot of problems, we won't be super specific about plugging these units in. Okay, we'll be able to tell what we're looking for right off the, at the end of it when it's all said and done. But I just want to show you how these combine here. Okay, so putting things together then, dA over dt is just equal to, we've got a 2 times a 3, that's a 6, pi, and then cm times cm we'll say is centimeters squared over seconds. Okay, we're talking about the change in area, so we'd expect units squared. Okay, and what this is telling us then is when the radius is 3 centimeters, okay, our area is changing by 6 pi centimeters squared per second. Okay, that's how those two rates are related here. All right, so that was an example of a basic related rates question. What we're going to do with the rest of this lesson is get into some specific types of problems that kind of come along with some specific tricks for making them work. Okay, so specific problem types, but as you'll see here, there's a lot of different ways we can generalize kind of these problems into many different contexts as we go through. Okay, so for example, here in problem 2, we're talking about boats, we're talking about bikes, there's a bunch of other different situations we can kind of apply the same process to here. Okay, we'll call this the right triangles, or I suppose I could say Pythagorean theorem question. Okay, let's say that ship A is traveling due west towards a lighthouse at a speed of 15 miles per hour, and ship B is traveling due north away from the lighthouse at a speed of 10 miles per hour. Okay, we're going to draw a picture before we go any further with this. Now, AP exam time, my bet would be is they'd give you a picture along with this. They want to test your knowledge of calculus, not whether you understand nautical navigation or anything like that. So we'll make a simple picture. I'm going to throw a lighthouse on some rocks right here. We'll say that's what a lighthouse looks like. And I put it there because ship A is traveling due west towards it. So in other words, it's coming to the west at my lighthouse like this. We'll call this my ship A. Should have left a little more space in there. And then ship B is traveling due north away from the lighthouse, so it's going north away. We'll say this is my B here. And we have some rates, which I'm not actually going to put on this picture. Let's just call the direction left and right the x direction. And we'll say up and down is the y direction. It doesn't matter which letters we pick, but then we're kind of thinking in terms of coordinate systems, which could be helpful for this. We want to find the rate of change in miles per hour of the distance between the two ships when ship A is 4 miles from the lighthouse and ship B is 3 miles away from the lighthouse. So in other words, we want to find this direct distance between the two of them. We can call that relationship whatever we want. I'm going to call it z here. Okay, d would also make sense, but we're doing a derivative, so dd over dt doesn't sound quite as nice. And what we're looking for, again, is that rate of change of the distance between the two ships. So what I'm shooting for here with this one is dz over dt. Okay, the rate of change of this length with respect to time t is my goal for this one. Now, before we go to set up an equation, let's list out what we know. Okay, what we know, and there will also be some things we might want to find right off the bat here. Okay, first thing I have is we're looking for the rate of change of this distance when ship A is 4 miles from the lighthouse. So in other words, when my x here is equal to 4, and we're talking related rates, so if I know x, I probably also want to know dx over dt, or I probably need to know it. And that's given me right off the bat. Okay, ship A is traveling due west towards the lighthouse at a speed of 15 miles per hour. So I'm going to say that that rate is 15, but I'm going to call it a negative 15. All right, because since this distance is going to be shrinking, getting smaller as we're moving towards the lighthouse, okay, that rate of change is going to be negative. Okay, and that will be part of the final answer, whether it's shrinking or getting bigger, kind of taking care of those positive, negative signs. We can do the same thing for the y. Y is equal to when ship B is 3 miles away. And dy over dt, we're given how fast this ship B is traveling. That's 10 miles per hour. And then the last thing here is z. Now, maybe I need to know that, maybe not. We'll kind of see what happens with our equation after we differentiate it. Probably, though. So what I can do to find that z when x is equal to the 4 and y is equal to the 3 is we can just use Pythagorean theorem. We can use 4 squared plus 3 squared is equal to z squared. All right, so in other words, 16 plus 9 is 25. 25 is equal to z squared. Square root, we end up with z is equal to just a 5. Again, something to recognize, this is just my 3, 4, 5 right triangle. Okay, just like that's going to show up on an ACT for you, I guarantee it shows up somewhere on the 3-hour-long AP exam. Okay, so we also have that z, which we weren't given, but we can solve for. And I'd say we also want dz over dt, but that's what we're looking for, so we'll kind of save that for our next step here. All right, next thing we need is an equation to relate the x, the y, the z all together. Well, once again, we're talking right triangles, so I can just use Pythagorean theorem. We can use x squared plus y squared is equal to z squared. And if I differentiate this in terms of t, I'll get my dz over t on the right side. Everything on the left side will be things we can fill in. Okay, so we should be able to figure out what that rate is here. Okay, so finding derivatives. Derivative of x squared is going to be just a 2x, but we're going to multiply by dx over dt. Okay, again, because we're not looking for the derivative with respect to x, we're looking for it with respect to t here, so we do need to use implicit differentiation. Okay, plus same thing with the y, there'll be a 2y dy over dt. And I said dt, I know I said it, but I wrote dx, didn't I? Oops, typo here, let's fix that. dt, and with related rates, you're typically always looking for derivatives in terms of t. And then same thing on the right side of the equation, that's just going to be a 2z using my power rule times dz over dt, the derivative of z with respect to t. All right, now something to keep in mind here, what the heck am I looking for? I want to know the derivative of this distance z in terms of t. Well, I've already got that out in my equation here. Okay, so it's good to kind of keep track of that. That's what I'm going to be trying to isolate in my next couple of steps. Okay, and then just plugging things in. I'm not going to worry too much about the units here. Okay, we're talking just a velocity, so miles per second. Plugging in what we know then, we've got 2 times x, which is 4, times dx over dt, which is the negative 15. All right, plus 2 times the y, which is a 3, times dy over dt, which is my 10, is equal to a 2 times the z, which is the 5, times dz over dt, which we don't know yet. That's what we're shooting for. And then what this problem turns into is just an exercise in algebra, okay, isolating this dz over dt. Just like you can solve for a z, you can solve for a derivative, which we've done before with implicit differentiation. Okay, do the arithmetic here. We'd end up with a negative 60 on the left side is equal to 10 dz over dt on the right. And when I divide by 10, I end up with, as I run out of room here because of my face, dz over dt is equal to negative 6 divided by 10 would be a negative 6. And then again, we're talking velocity, so that'd just be miles per hour. All right, so there's an example of a related rates question involving right triangles, Pythagorean theorem. Okay, now the trick is when you come across another one of these, you don't have to kind of do this all from scratch. I'm not doing the same thing. I've already seen how to do these problems before. You just have to be able to recognize that we're talking about a right triangle problem and then essentially just apply the same process to it. All right, so part B is the same idea. Instead of talking about boats, we're talking about Bill and Ted and an excellent bike adventure here. Go ahead and pause the video, see if you can work through this one. Now, one thing for you, we switched up in class instead of 1 hour, let's say a half hour, just because there's otherwise a kind of nice phenomenon that works out. It works out a little nicer than I'd like it to. Let's make sure that doesn't happen with this half hour here. Yep, so again, pause the video, work through this one, give it a shot, and we'll work through it together once you give it a shot here. Don't just watch me do it. Make sure you're trying these. All right, so let's go ahead and run through this. Again, hopefully you did try this before you're watching for the answer here. Bill and Ted leave an intersection riding bikes at the same time. Okay, Bill's traveling north at a speed of 12 miles per hour, so Bill is going north. Ted is going east, it says. And then once again, how fast is the distance between them changing? Okay, well, if we call Ted's direction the x direction, Bill's direction the y direction, we can say this is just my z direction again. And once again, we're looking for dz over dt. And we'll have a lot of similarities with how we set this problem up. All right, what we know? Well, we know that x, or we're looking for when x happens, shoot, it doesn't give us the x. How fast is the distance changing between them after half an hour? Well, we're not given the x explicitly, but if we're going 10 miles per hour for half an hour, that would be 5 miles. Okay, so x is 5, dx over dt, then the change in x is the 10. Now notice with this one, that is a positive 10 because this distance is getting bigger as we go. And the same thing with the y. If we're going 12 miles per hour for half an hour, that'd be distance of 6 here. Okay, with dy over dt equal to the 12. And again, since that distance is growing, that'll be positive as well. And then once again, we can find the z with this one. Okay, we will need it, as we kind of saw with the last problem. We can say that our 5 squared plus 6 squared is equal to the z squared. Okay, so in other words, z is equal to the square root of 25 plus 36, that'll be a 61. And then that's not a perfect square, that's going to be an ugly decimal. Let's just leave this one as square root 61 for now. Okay, what I don't want to do is round this and then throw off my final answer because I rounded too early. Okay, so we'll leave it in this radical form. All right, so we've got what we know. We know what we're looking for. Again, this is just the right triangle problem, so we're going to use the same equation, just Pythagorean theorem. X squared plus y squared equals z squared. And the derivative is going to work out the exact same way. It'll just be a 2x dx over dt plus 2y dy over dt is equal to 2z dz over dt. And once again, that's what I'm looking for, that dz over dt. We can just plug everything in. So we've got a 2 times the x5 times the dx over dt, which is a 10, plus 2 times the y6 times the dy over dt, the 12, is equal to 2 times the z, which is that root 61 we found, dz over dt. Combining everything on the left, I get a 244 is equal to just the 2 root 61 dz over dt. And if I divide both sides by that 2 root 61, I'd get half of the 244, which would just be a 122 over root 61 is equal to my dz over dt. So we could leave it like that as an exact answer. All right, or I'm thinking AP exam time, problem with some context, they're probably going to have you round it. This number really means nothing to me. If I plug this into my calculator, I'd end up with a 15.620. We'll go 3 decimal points just like on the AP exam. And then once again, we're talking miles per hour as we run out of room here. All right, so let's say that's enough calc for the day. That covers homework 1 through 3, so it's only 10 total. Give you a good start. Start working on that, start plugging away at it. We are going to build off this stuff with the next video. So yeah, do make sure you give it a chance as soon as you can. We'll catch you next time.